Well, hello, standard geometry students, and welcome back to some online math. I wish you were here because it's my tradition every year to pass out candy on this day because it's my birthday. And I always pass out candy on my birthday for all my students, but you're not here, so now Miss Sarp's gonna have to just eat all this candy by herself. But I do have a couple other people that I got for my birthday. They're a little better than the bunny, aren't they? I thought they were pretty cute. Okay, let's get started, and they'll come back and help us to learn some other things here in a little bit. Another thing that I got, a brand new board. Isn't this exciting? So we're going to go ahead and learn 12.4 and 12.5 this week. So 12.4 and 12.5 this week. Okay, let's go ahead and get started on 12.4. I feel like I'm kind of in my element again, okay? So on 12.4, we start out with that same thing that we had from before, that central angle, okay? So you have the central angle because, remember we had that in our assignment last time, the vertex is at the center and the two sides are the radii of the circle, exactly. So today we just start out with another new term, the intercepted arc. The intercepted arc is just saying here, look at these two sides of the circle, and it's the arc that's in between them. Okay, so that's what an intercepted arc is. So it's just like continuing on with the sides of your circle and saying what's in between them. So we have the formula then for the central angle. We know the central angle is always equal to the arc. So angle equals arc. So that's my central angle. Now, believe it or not, this is the one that you end up missing as we get going on this today because of all the other angles. So this 12.4 and 12.5 are a lot of just angles altogether. So I just want to make sure that you remember the central angle is the same. Central, same. Okay? Now, what happens today then is we get into a second kind of angle called an inscribed angle. Now remember inscribed polygons, because it's really kind of the same thing. If you were to put this as another segment here, it would become an inscribed triangle because every angle has its vertex where? On the circle, exactly. So if you look at that in comparison, you can see that it could not be the same because if I came out here and had the same intercepted arc, this angle is not the same size as this angle. And you can almost see the comparison. So what you have here is our first theorem, and I know I'm going to have a little bit of a reflection down here. I tried to explore with how to get rid of that, and it's just going to have to be there, but we'll read it and hopefully you can see it. An inscribed angle is half the arc. So I like to write that as angle equals half arc. So looking at that, that's all the new thing is in this 12.4. It's that simple. All I have to do is say, well, what arc am I talking about? And we're back to that same thing we started with on our definition. It's the intercepted arc. So if I have that intercepted arc, then I'm just going to say the measure of angle 2 then, because those are the sides. Now, no longer are they radii because it's not a central angle. It's an inscribed angle. Its vertex, remember, determines where it is. So the vertex is on the circle, makes it an inscribed angle, okay, where the two sides are chords. So the measure of angle 2 then would just be 1/2 of 50 degrees, or the measure of angle 2 is 25. Now that's really as easy as 12.4 is, okay? But what happens, because they'll give you sometimes an inscribed angle, and then they'll give you the angle. So let's say that they give you this angle is 55 degrees. And then they want to know what is this arc. Well, again, you still identify the intercepted arc. So angle on the circle comes out. The intercepted arc is this. And I like to work it exactly the same way. So I see the exact same formula, angle equals half arc. So I just go angle 55 degrees equals half What's the arc? And I just let the algebra do the work for me then. So if I do that, half of x, well, I can't take half of x. So I have to undo by multiplying by 2. What I do on one side, I do on the other. Okay? So obviously then x is 2 times 55 or 110 degrees. So it makes sense. If you're going with the angle, you're going to say half the intercepted arc, and then basically you're doubling it on this side. But you use the same formula. 55 equals half the x. So what happens then if I have a special circle on that? Whoops. If I had a special circle called a semicircle. So what happens if I have a semicircle and then I have an inscribed angle in a semicircle? Okay? My nice new birthday present is being really kind, but I didn't make it not to go, so I should probably put the brakes on it here, huh? Okay, so what we're going to look at then is to say we could inscribe a circle where I end up giving you a semicircle. So remember, a semicircle is determined by a diameter, so look for the diameter there. So now we're saying what happens if I inscribe an angle in the semicircle? So what happens if I make it on the circle like this? What would the measure of angle 3 be? Yeah, it's really a matter, again, of just looking at the intercepted arc. Oh, angle 3 starts and stops on the circle here. So obviously the intercepted arc is what? A semicircle of 180 degrees. So what would the measure of angle 3 be? You're exactly right. The measure of angle 3 is 90 degrees. So they write this as another fact, so I put that down here, but I really don't know that you need that fact. An inscribed angle in a semicircle is always a right angle. So if they give you something here with some variables on it, then I can just set whatever that is equal to 90 degrees. Okay? Now, what happens if I have an algebra problem and I say, let's just give one circle and let's make an inscribed angle here and say this inscribed angle is 3x degrees. Okay, and then I make another inscribed angle, and this inscribed angle is 2x plus 20 degrees. How can I find x in that? You see, you really don't need too much of another theorem. You just recognize the vertex is where? On the circle. You look for the intercepted arc, so that intercepted arc becomes very important. And you say, oh, that intersected arc is right here. Well, look at this. If that's that intercepted arc, wouldn't this also have the same intercepted arc? So we really don't care how many degrees this is. Because if this angle has the same intercepted arc as this angle, what can you tell me about these two inscribed angles? And that becomes our third theorem. Two inscribed angles that have the same intercepted arc are congruent. So as soon as I see the two inscribed angles here having the same intercepted arc, I really just have a shortcut in that theorem and say, all I have to do is set this angle equal to this angle. So I would solve for x by saying 3x is equal to 2x plus 20. Subtract 2x on both sides, and I have it solved. So the pictures will look a little more difficult, but they're really not too bad. If they have the same intercepted arc, then the angles have to be the same. Would there be any other inscribed angles there that would be the same? Okay, you think about it, you go backwards. Okay, I could see them right here as well. Now I don't have any numbers on here, but these two angles up here would also have to be the same. Okay, so sometimes it's tricky to find those intercepted arcs, the intercepted angles, inscribed angles that would have the same intercepted arc. So you might have to turn your circle around a little bit. Okay, now our last thing in 12.4 says, okay, I've got all these inscribed angles. what happens if I go back to what we had in another chapter? What happens if I make an inscribed quadrilateral? Well, remember quadrilateral has 4 points, so let's just make them like this, so they're not anything in particular. So if I say I want A, B, C, D, an inscribed quadrilateral. It's an inscribed quadrilateral because it has 4 inscribed angles. The angles are on the circle and the 2 sides contain chords of the circle. So every single one of these would be half the arc. So I could look at it and say, where's angle A? Well, angle A is right here. Where's the intercepted arc? All the way around here. Okay? So A would have to be half of this intercepted arc. Everybody agree? Okay, now look at it in terms of the other side. What happens if I say, let's go over here to C? It's also an inscribed angle. So if I go over there, then I'm saying, oh, well, the ends of C are at B and D. Oh, look at that. So that's where we get to our next point, because now look, this arc, this intercepted arc, and this intercepted arc make a whole what? And you know the whole circle has to be 360 degrees. So since the angle is half the arc, it's half of this, it's half of this, and half of 360 would be 180 degrees. So all we're looking at here is the measure of angle A plus the measure of angle C has to equal 180 degrees. Likewise, we could do the same thing here. B and D are opposite angles, so I could also say the measure of angle B plus the measure of angle D equals 180 degrees. And that's our last fact here in 12.4. Opposite angles in an inscribed quadrilateral are supplementary. Opposite angles in an inscribed quadrilateral are supplementary. So the questions there become pretty simple. They say, okay, what if this is 120 degrees? What is the measure of angle C? We'll put a 2 in it. You're exactly right. The measure of angle 2 would be 60 degrees because they have to add up to 180 degrees. Okay? Opposite angles have to add up to 180 degrees. And I could go with any of the opposite angles, so I could have done the same thing with B and D. If I said this is 100 degrees for B, what would D have to be? You're exactly right, 80 degrees. Okay? Well, that's 12.4. It's really just about inscribed angles. Remember, the inscribed angles have the vertex on the circle. The sides are 2 chords of the circle, okay? And they're always half the intercepted arc. So that's the big part, half the arc, okay? Now, the 12.5 was so similar, and I'm going to make it very, very easy in just looking at 3 facts, okay? And so this should go very, very quickly because one of our facts is really just what we just did, okay? And that is what we have here. What kind of an angle is that? Right, we're still looking at an inscribed angle. You see how its vertex is on the circle? Its intercepted arc is here. So I'm going to just divide this into 3 theorems. If the angle is on the circle, like the inscribed angle, but we'll expand it, then all I have to say is angle equals half arc. Exactly what you said on the inscribed angle. So angle is half the arc. So if I wanted to find the measure of angle 1, let's say this is 40 degrees, what would the measure of angle 1 be? You're exactly right. The measure of angle 1 is equal to half of 40 degrees. And of course, half of 40 degrees, 20 degrees, and you'd be done. Now that's exactly like it was in 12.4. That's why I said 12.5 is going to be pretty easy for us, because now all we're doing is saying, hey, I could make this where it's not just 2 chords, but I could end up with a tangent okay, as one of them, and say my vertex is still on the circle. Okay, so it doesn't matter where it is, I'm just saying my vertex is on the circle. So now let's take a look at this one. Be careful on your assignment because sometimes they'll have some review. If that chord went right through the center, then what do I have here for the intercepted arc? So my intercepted arc is still, I don't have to tell you, it's already there, 180 degrees. So what would the measure of angle 2 equal? Half the arc. Exactly. So the measure of angle 2 is half the arc. If the arc's 180 degrees, then my measure of angle 2 would be 90 degrees. Okay? What happens if they give you this arc, but they ask for this angle? Well, I still do the same thing. I say the angle is half the arc. So I have to look at this angle and say it's half of this arc. So this side would be 50 degrees. Now, how am I going to work that if this angle is 50 degrees? You see how we have a review in that? Okay, so you might have to find one side of the angle and then find the other. So remember those were linear pairs. And what do you remember about linear pairs? They're supplementary, exactly. So the measure of angle 3, I'm just going to look at it and say it would be 180 minus 50, or 130 degrees. Now you could do this a couple of different ways. So what you could do is you could find the angle that is the intercepted arc on this, or you could say, well, if this is 100, then this whole arc would be 360 minus 100, or 260 degrees. Well, isn't that the same? Half of 260. Okay, so there's going to be some review in that, and that doesn't matter. You're still going to be looking at saying the vertex is on the circle. So our big thing here, our big idea here is when the angle, the vertex of the angle is on the circle, the angle is half the arc. What if it's on the inside of the circle? Now, if you think about that, let's say this is 100 degrees, and this over here looks a lot smaller. Let's say it's only 30 degrees. Would it make sense to say angle 1 is equal to 100? Well, remember, there's an X here, so those would be vertical angles. So could this be 30 and this be 100? No. Any ideas what you're going to do? Very good. I'm just looking at it and saying anytime the angle's on the inside, my angle equals half one intercepted arc plus the other intercepted arc. So that's our big idea for the second one. If it's on the inside, I do half of arc plus arc. So here, the measure of angle 1 is just 1/2, 100 plus 30. Well, half of 130 would be 65 degrees. And that's all I have to do, okay? So all we're looking at is if the angle's on the inside. Now you may say, but Miss Ark, what happens if it's a central angle? Well, you could do that because if it's a central angle, its vertex is at the center. Your vertical angles still have to be congruent. So you could say these two arcs are the same. Usually we don't because we don't want to average them if they're the same, okay? But it would still work, okay? What happens if I give you this one is 80 degrees and this one is 200 degrees? And it wants to know the measure of angle 2. Well, again, find the angle where the intercepted arcs are. So if I have this and this, I could find this angle. Make sense? So I could say this angle is half of 200 plus 80, or 280. So this angle is 140 degrees. So what would angle 2 have to be? See? Again, you might have some review in that. It's still saying it's on the inside, so I'm going to do half of arc plus arc. So half of 80 plus 200, okay, or 140, and then the measure of angle 2 would be 180 minus 140, where the measure of angle 2 would be 40 degrees. So the big thing there is anytime it's on the inside, half of one arc plus the other arc. Inside, add the two arcs. On the circle, just half the arc. Okay, so we only have one other possibility, and that way we don't have to worry about whether they're two secants that make it, or two tangents that make it, or one tangent and one secant that makes it. You're still looking at it and saying the angle has the vertex on the outside. So I like to think of it like this. If it's on the inside, if it's on the outside, those are two opposite things. So I just do the opposite operation. So here I said the angle is equal to half arc plus arc. Here, arc minus arc. And to be logical there, we have to say big arc minus the small arc, because we already know you can't have angles that are different degrees. So it's as simple as this, guys. If I say this is 50 degrees and this is 20 degrees, I look at the intercepted arcs again, and I say, here's my angle. So what's in between them? These two arcs. And I do just exactly what I said up here. I say my angle, so the measure of angle 1 is equal to half big arc minus small arc. So the measure of angle 1 is half of 30 degrees, or the measure of angle 1 is 15 degrees. Okay? So the big idea here is on the circle, angle equals half arc. Inside the circle, angle equals half arc plus arc. Make sure that you go opposite so that my intercepted arcs are right across from those vertical angles. If they're not, you have to find the other angle and then use the supplement. Okay? And here it's just big arc minus small arc, so it doesn't become negative. Okay? So let's say this is 260 degrees, and it says to find the measure of angle 2. Well, on this one you got a special case, so I wanted to make sure you had that. This one, when it's two tangents, you already have both arcs if I give you one. Because remember, the whole circle is how many degrees? So even though it didn't tell me this second arc, I could find it, it'd be 100 degrees. Okay, so really I'm doing exactly the same thing. Vertex on the outside, so the measure of angle 2 is half big arc 260 minus small arc 100. So the measure of angle 2 is half of 160, or the measure of angle 2 is 80 degrees. So again, the big idea, angle equals half arc minus arc. Now, our last thing here is what happens if they give me the angle, let's say it's 50 degrees, and let's say this is 60 degrees, and they want you to find x. Now x is on the arc. How am I supposed to do it if it's on the arc? Last example, and then we'll get into some that you can just copy down. Okay? You still just look at your intercepted arcs. It's as simple as that. And you just use the same formula. So now I put it in for the angle. The angle is 50, and I say 50 equals half big arc, remember, minus small arc. So my big arc would be x minus my small arc, 60. Now I like to get rid of the times 1/2 first by doubling, so it makes it a little bit easier. So I just double both sides to cancel out the 1/2. So I have 100 equals x minus 60, and then just add 60 to both sides. So let the algebra do your work. Now I'm going to give you some more examples of that on the reteaches here. So the big idea that I want you to understand here is just look for those three things. Is the angle on the circle, just like the inscribed angle?